Okay, it's the final lesson in the circuits part of this topic. And some starters. Okay, and I'm muting there. Fairly straightforward questions. If we look at the formula, these are the formula that you need to be able to use and apply, particularly higher levels of interchange between them. If you're unsure on this, then you need to go back to previous lessons. Why is electrical power transmitted at high voltage? Low current, because power loss is proportional to current squared. Okay, so this lesson is pretty much aimed at very much higher tier end of things. So let's move on. Voltage or potential difference. Okay, we've talked about this before. Voltage is measured in volts. And if we look at the top of the cell and the bottom of the cell, we have a potential difference across there. Now that tells us about the amount of energy supplied to the current which is flowing there, the coulombs of charge which are flowing across. And in this case, we have a 1.5 volt potential difference. Okay, so that's pretty much telling us the amount of energy. Okay, so we considered a 1 coulomb charge. That's that little blue blob there. And as we started moving around, it starts off with 1.5 volts and ends up with 0 volts. Okay, so as it's flowing through that circuit, it's actually transferring energy, it's doing work, and it finishes with 0 volts, so it's done work. So the potential difference tells you how much energy is transferred for each coulomb, and that's what potential difference voltage is. In this case, each coulomb there had 1.5 volts, which means that 1.5 joules per coulomb was being used. So in general, 1 volt means 1 joule per coulomb. Okay, to get your head around that. So it starts off with 1.5 joules, dissipates it and ends up with 0 joules, and that's the potential difference. So there's our definition, and from that definition we can get our formula, because we've just defined there, we've just said that a volt is a joule per coulomb. The word per means divided by, so we have now a little formula that says voltage is the energy divided by the charge. And we can write it as a symbol form like that. And with our quantity symbols and units now complete for electricity, there they all are there, and that's where that sits. So if you want to pause that and make a note, that'd be good. Okay, but I'm moving on. Okay, so let's apply this. Electric kettle, we know its voltage, we know how many coulombs of charge are being transferred over a certain amount of time, and the first one is how much energy is being transferred. We know that V equals E over Q, we rearrange it, we substitute our numbers, and we get our final answer. And in this time I've written it in kilojoules because I don't like writing all those zeros out. Okay, so we know how much energy is being transferred, so now we can work out the power, which is just energy over time. And that gives me an answer in kilowatts. Okay, so this is a typical middle to higher sort of tier question, where it's in 2 steps, where we're taking our result from our first step to solve the overall question, which is what is the power of that kettle. So pause that, write it down as an example, and I'm moving on now. Okay, here's the second question. We've got a plug, we've got a cooker plugged into the mains, 230 volts, and it transfers that amount of energy. How much charge was transferred? First of all, then, we're applying our formula, we're rearranging it to get E over V, and we get an answer of 3,134 coulombs. Okay. So what was the power? Well, we know the energy that was supplied, and we know that was supplied in 1 hour. Okay. So therefore we're just applying our power energy time equation directly, and we get an answer of 2 kilowatts, which sounds sensible. Okay, when we're talking about heating elements and heating devices, we're only talking about a couple of kilowatts. And finally, this is a bit of a weird question, and it says how many electrons are actually moved. Now we know an electron has got this amount of charge, it carries a tiny amount of charge. So very simply, we know the charge that was transferred was 3,134. Oh no, 31,304. I do apologise. And we know the charge on one electron, so we get that many electrons being transferred, which is quite a big number. That's a 2 with 23 zeros after it. Okay, so electrons carry a tiny amount of charge, and when we operate appliances, we are transferring billions and billions of electrons. Okay. So the challenge here is actually application. Now if you can get hold of the document, there is a document that looks like that, like the picture there, with the questions on. If not, just pause this screen for a moment so you can actually do the questions, and then we'll go through the answers. Okay, so first one, straightforward application to find the voltage. Second one, how much charge was transferred, so we're reapplying it, and there's an example there, and there's the answer there. And the third one, we are finding the energy. So if you've done these first three and you've got them correct, that's what these questions are after. So can you rearrange the formula to get the three different forms of it? Next question is applying it to a real life situation. So we have a lightning strike, which transfers about 1 billion joules. Now, we should know that billion is 1,000 million, and that's that number there. Look. We've got the voltage of 300 megajoules. Mega means million. So how much charge gets transferred? And then we get our answer. We rearrange our formula, put the numbers in, and we get 0.3 coulombs, which I thought was very small. So I had to go and research this. And yes, that's pretty typical, because even though we've got big voltages and we've got big currents flowing, they're only flowing for a minute amount of time, so we have very, very small number of coulombs being transferred. Okay. Number 5 was asking about an electron, and it's gained this amount of kinetic energy. What voltage caused this? Well, this is an application of conservation of energy. So the reason that electron accelerated was because of a voltage, and voltage is joules per coulombs. So we just take that as the energy. So that's the kinetic energy there, and we divide that by the charge, and that gives us the voltage that did that. So in other words, if we got an electron and we placed it at a 2 volt, 2 volts for cell, and let it go through to 0 volts, it would accelerate and it would gain that amount of energy. Okay, so these questions get a little bit more cognitively demanding. Now the next questions, these are quite challenge questions, very much higher tier. So either pause it or get hold of the document. It's in the document, but I'm going to move on now. In fact, I'm going to move on now. So here we go, we've got an electric car, it's operating at that amount of kilowatts. These are all realistic figures, by the way. I looked up these. This is a Tesla car. How much energy is transferred in 45 minutes? Well, the challenge here is to turn 45 minutes into seconds. We know our power. Power is kilo, so 100,000. There we go. And then we get an answer of 1.6 times 10 to the 10 joules. How much charge was transferred? Now we've got a value for energy. We can apply this formula. We've got our energy that we just worked out. We know the voltage is 500, so we just do the sum there. And we've transferred that number of coulombs. And what current flowed over this time. Now this is bringing up the formula, I think it's the first one that you come across in electricity, which is current equals charge divided by time. This is why it's a high level question. It involves multiple formula. Okay, we just plug those numbers in that we've already calculated and we get an answer of 200 amps. Okay, so you can see why this is a high level question. Moving on to the next one. It's the toy drone, charged by USB. How much charge is transferred? Simple application of that formula. How much energy is stored? So now we have a value for charge. We can use this formula, E equals Q over QV. And we can calculate that it's used this amount of energy. Okay, and then finally the drone. It has a mass of 0.5 kilograms and it's sent vertically into the air. So it starts off at the bottom, goes up into the air. In theory, how high could it go? So this once again is applying a formula from another topic, in this case, E equals mgh. This tells you the energy something gains when it goes to altitude. We've rearranged it to find h is equal to E over mg. Now we know the energy that can be stored in the battery because we just calculated that, which is here, and we divide it by our mass times our gravity, and in this case I've taken gravity to be equal to 10, and we get an answer of 144,000 meters, 144 kilometers, which would be in space. I mean, in reality that wouldn't happen because of efficiency issues. Okay, so this is very much a very high level question, that one. So let's move on. So really that's it for the electrical formula in this lesson 12. The next couple of lessons are about static electricity and charges. They're more, qualitative. So here we go. For this topic, and to be successful at the higher tier, you need to be able to recall all the different equations and to be able to intermix and rearrange them, okay, to find solutions. And one thing you should always be doing is setting out your solutions neatly and logically so that your examiner can follow. Okay, and I hope to show that in the previous examples. So, enjoy.